was given. Okay, and I need to find the global max and global mean, but specifically in one region is given also. So subject to these constraints is the function is given, that one. And so we are doing something, no? We are doing, remember, we start similar to the without constraint. You find the critical value. Okay, the critical value is when the gradient is 0. So gradient 0 means the partial derivative equal to 0. You differentiate with respect to x, you differentiate with respect to y, you put equal to 0. In this case, you get super easy linear system of equation, and you solving, and the answer was 1,1. Are you recording? Yeah, I am recording. Yes. Let me check it just in case, but I suppose I click. Yes, it's recording. Thank you for reminding me. So I determined the point 1,1. 1.1 is located here. 1,1. Okay, here this is the point I include inside the list. So you navigate for the boundary. Remember the idea for the no apply second derivative test. No, because this is global. So now you navigate for the professor. Remind me about your information. Okay. It's the thing. Quick. Theo, remind me que we discussing about. Remember that the first day I say that the final test is mandatory. Some students say que in the syllabus no specification this or it's completely backward. No, it's okay. Okay, the final test no mandatory. It's only one tool que I create for the students que need to improve your grade. Suppose que you are no good grade in one test. You take the final, the only disadvantage is community. So everything together, chapter 1, 2, 3, and 4 together. And 10 questions, written test. No online. Online is only the classical 1, 2, 3, and 4. That's it. The final is written also, community, no mandatory, only help the student. The student can get A in every test. You don't need to take the final, okay? Clear? Answer me. Clear or no? Okay, cool. So let's continue. Yeah, no more comment, guys. Focusing in the mathematical part. So now I navigate for the boundary. The boundary is one dimension. The region is two dimension. For example, you navigate for this path. I want to call y equals 0, no? Because it's on the x-axis. So now my function, original function, x comma 0, because I declare y 0, no? You plug in 0 here and you get x squared minus x. Yeah, I don't know why I like to call f1. It's a function of x only, and it's a calculus 1 problem. Bueno, you evaluate important in any endpoint, exactly like a calculus 1, but you evaluate in the middle also. So to evaluate in the middle, you have infinity value. No, the critical. So you compute the first derivative. Is 2x minus 1. Put equal to 0, and x is 1/2. So we have 1 point, including the list, is 1/2, 0. And also, I know, you evaluate in the endpoint. In the endpoint is, well, f evaluating 0, 0 is 0. Okay. And f evaluate. Test number 2 is do 20. Okay, it's 20. Entonces, it's okay, 20. 20. Entonces, we have time. The problem is that when I finish the review, well, entonces we start new chapter, no? Because I don't want to stop. Never. Okay, entonces 20. Super. Much better for you. No 15, 20. 20 is next Monday, no? Next. Oh, we have time. Good. We have time. Entonces, okay, no more blah, 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 blah. Focus in mathematics. Now, you use 5,0. You evaluate, don't forget, evaluate in this corner. This corner and this corner. I did that. And the answer is just plugging in the original equation, no? The answer is 20. Okay, good. I finish the part que I highlight in red color. Oh, noise. Where's noise? Guys, it's hard to focus in the... Okay, now I'm moving on. Either way, you select any path. However, I want to go rotate the figure in counterclockwise, and this is the equation x equals 5, no? X equals 5. It's very good. Now you find the equation of this. See, it's a line inclination. You need to find a slope, equation of the line. Okay, so now you evaluate f and phi comma y, no? Because y in this case is a variable. So plugging in here, and we have 25 plus 2y squared minus 5y minus 5 minus 3y. We combine like term, and we get 20 plus 2y squared minus 8y. Yeah, I call this guy like f2. It's function only of the y. Okay, now you evaluate in the endpoint, and you evaluate in the middle using the first derivative in order to find minimum or maximum local. So you find the second derivative to with respect to y is 4y minus 8. 4y minus and force it to equal 0, y is 2. This is our famous point. Is the point 5,2, no? 5,2. 5,2. Now, the endpoint. Well, the endpoint actually, I did that. So they are coincidence. The red part and the green part share the same corner. I don't need to evaluate the green. So you evaluate now f in this corner is 5,3. 5,3. 5,3, I did that. The answer is 40. Okay. So the function value in the corner 5,3 is 40. Okay, let's continue. No. We navigate now. Suppose blue color in this path. Okay, we travel in this direction. Okay, so now it doesn't matter. It's not important. The direction is irrelevant in this case. This is the y equals 3. And use substitution in the original equation. X is a variable, 3 is a constant. We plug in, we apply algebra, x squared plus 18 minus 3x minus 3 minus x, minus 9. Okay, so we combine like term, and the answer is x squared minus 4x minus 9. Yeah, I call f3. Okay, depending only on the x. Okay, and likewise, we find the derivative. Okay, is 2x minus 4 equals 0. And x is 2. And the famous point is the point 2, something. 2,3, no? 2,3. 2,3 is approximate here. Okay, let me mark the point, 2,3. I forgot 5,2. 5,2 is green. And here 5,2. This is an important point I need to consider in the last moment to evaluate the function. Now. Hey, I forgot in red color. I forgot 1/2, 0. 1/2, 0 is here approximately. 1/2, 0. Okay. This is one way I create the organization. It's too long problem, but it's easy. Finally, well, you navigate down for, let me using another color, maybe purple color is good, to this path. I forgot something. I forgot evaluate and the well, I did that in the green part, but I need to do this in the blue part, 0,3. 0,3, the function is 9. You plug in it, 0x 3y. Okay, let's move on to the last segment. Purple color. And this direction, well, now it doesn't matter the direction, it's not important the direction. And now this is x0. Plugging in 0 in the original equation, the function 0, y is a variable. So we have 2y squared minus 3y. I call this f4, depending on y. You differentiate, is 4y minus 3 equal to 0. So because y is 3/4. And the point is the point 0,3/4. 0.75 approximately. This point like this is 1, 0.74 here. 0,3/4. Okay. When you finish this analysis, this is the most important moment. You are doing the list, the famous list. Okay, always we finish in the optimization problem with constraints. And you evaluate in the famous, how many points total we have? I suppose we have 9. Let me see, 1, 2, 3, 4, 5, 6, 7, 8, and 9 points. Why 9? Because we have 2. Well, we have 4 corners. We have in the middle of the segment, we have one potential, max, min, local. And we have in the middle of the region 1,1. So in total we have 9. And this is the long way. Can you evaluate one by one the original function? I did in some, but not into all. 1,1, the answer is negative. 0,0, I did that. The answer is 0. F and 5,0, the answer is 20. Okay, one more. F and 0,3, the answer is 9. F and 5,3, the answer is 14. F and 0,3/4, the answer is negative 9/8. And F and 1/2, 0 is negative 1/4, negative 1/4. And F and 5,2 is 12. 5,2 is 12. And F and 2,3 is 5. Let me count how many. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now this is the, we finish. What is the local mean? Look, global mean, sorry, this guy. And what is the global max? This guy. End story. Es easy, eh? I know it's long, but it's easy. Yes or no? Everyone follow me? Question. Entonces, es important, extremely important. You, at the beginning, you suppose que you have no constraint. O sea, suppose que the domain is R2, X, Y plane. You determine the critical value. In this case, we have only one, but suppose we have more. And you take only the critical value que is inside the region. Si es outside, no. Si es outside, you discard. After that, you navigate. It's important, guys. For every boundary, you convert the problem into 2 dimension and 1 dimension. You apply calculus in any boundary. And don't forget to evaluate in the corner. And you list in any points. And you evaluate the original function. And you take the maximum and you take the minimum. And it's already super easy. I promise in the review we have another problem. A little bit more, not too long, but complicated. And you, in the review now you see everything clear. Because the review is, we come back again at the beginning, step by step. Relax, cool down. We review. Next idea. Okay. So I want to. Go ahead.
I have a question on this one. I get that you plugged in all like I guess the endpoints, like the corners. And to find their values. And then I get the how you found the critical value by setting the gradient equal to 0. I don't like, why'd you choose those 4 other critical values?
Because remember, okay, let me try to, okay, look, this other point is a point. Remember, this is a surface. This is surface. Now you analyze, you lost the information for the C. So this is surface X, Y, and Z. And this is surface, we are surface. Wow. Entonces now the constraint is this rectangle. I need to see in this rectangle what is the part of the surface, and you evaluate one by one. Because when you travel here, I don't know exactly what is the height of the C value in the upper part. Okay, therefore, because this is no constant. Actually, maybe the point is 1/2, 0 is a minimum. So, si you see, for example, C look like that. It's a minimum, right? This value is 0, 0, es 0. Es 0, sorry. And 1/2, 0 is 1/4, it's negative. Look, it's negative. And 5,0 is 20. Wow, increasing too fast is 20. Entonces, pero, okay, but I have no idea. I try to detecting si this local mean is the global mean. Okay, do you understand this or no?
Yes, I just
Sure. But let me try to. I create, in order to save time. I make a decision. Don't show you this, but I create one script in GeoGebra to illustrate very well everything together in 2 dimensions and in 3 dimensions. Let me show you. Let me try. It's coming. Okay, open. Open. Hey, this guy. Open this. Boom. Let me share the screen. Okay. Do you see? Do you see? Everyone saw there? Okay. Okay, this is look like similar to the paraboloid. Actually, it's not strictly paraboloid, but it look like similar. Okay, it's the equation. I just type in my equation here. Okay. However, look at that. If you if you see here, this is the XY plane, like that, no? XY, yeah, XY plane. You see here our famous region, no? Look at that. This is my region. Let me make it zoom to see more clear. And this is the point. Okay. However, using another instruction or command of the GeoGebra que I promise we see in detail in the last chapter, que es the command surface, que es very similar to the command curve, but in 2 dimensions. You see exactly what piece of the paraboloid lie exactly on the constraint. Look, let me show you, but in 3D. In 3D. Let me make it zoom. This is exactly the paraboloid. Look at that. I want to overlap both, but no. It's the piece defined inside this. And you see, when you evaluate, oh, look at that. This is the global max, que es el 5,0, que es 20. However, the local is in that point, that point was 1,1, right? Que actually is a coincidence. It's out. It's a coincidence que the local mean coincident with the global mean. More clear, Mr. No?
Yeah, I definitely understand like seeing it in 3D, and it makes the example make more sense.
Yeah.
But on the whiteboard, can you go to the whiteboard so I can ask the question?
Let me switch it to whiteboard again. Whiteboard. Let me know what part you don't understand very well. Okay. What part you don't understand very well? The boundary.
So when you chose y equals 0, x equals 5, and y equals 3, and then x equals 0, is that because those are like the points on the corners too? Like you kind of have to plug in like...
No, exactly. Not exactly. When you introduce this restriction, you convert my surface, okay, in 1-dimension problem. So you plug it in. So any z value, get the value of the function, coincident with the red or green or blue boundary, have one function, that function depending only of the one variable. So you want to study the behavior of this intersection, because in 3D you have surface, chung, and you have y equals 0 as the plane, and the intersection between the plane and the surface give me a curve. I want to study the z value, que es the height of this curve in 3D. To study this, I am doing the simplification. The simplification is plugging in y equals 0, exactly the same we are doing. Remember, two surfaces intersecting each other, and how you find the curve that represent this intersection? Well, you put together this equation, algebra, in this case it's easy because it's constant, and you get approximately the equation for the curve, okay? And now this curve, maybe we have a local mean or local max, but I don't care. I don't care. I say que es extreme value, and I put in the list. Because finally, I evaluate the regional function in order to compare with the global max or global mean. This idea is clear?
Yes. So you had to choose those numbers? You couldn't choose anything else?
No. When you navigate, when you navigate on the x-axis, it's obvious that the equation is y equals 0. When you navigate in the vertical line, x equals 5, que es the green, I declare x equals 5. And y, no, y is completely free variable. You fix it, x equals 5. X equals 5 intersecting somehow with my surface, que es this equation. Okay? Entonces, now, where come from this number? It's the equation for the boundary. In other more complicated scenarios, suppose in the review we have no rectangle. No, you have, for example, the triangle. So now suppose que this is x equals 0, okay. This is y equals 0, but this is equation, it's a linear equation, y equal mx plus b. But okay, but you see, you and the surface that you are analyzing, you stay x like a x, and y you replace for the equation for this line, so you get a new function depending only of the x, and give me somehow the z value of the surface intersecting with this plane. Okay? Yes or no?
Yes.
You think about that. Little by little, you understand. This is not the only example we are doing, guys. We are doing one more in the review. The problem is it gets too long, no? Okay. Okay, let's do it for the last topic. Okay, the last topic is Lagrange multiply. Lagrange multiplier. Boom. Lagrange multiply is another way to analyze another point of view. Yes, another point of view to analyze optimization when you have constraints. Pero another completely different, pero super efficiency. Wait, let me try to explain. It's a little bit to understand, a little bit hard to understand, a little bit hard to me explain. Suppose that we have the famous three-dimensional axis. Suppose also that we have one surface. I don't know, like that. A surface I want to call f of x, comma y. Of course, this is z. Let me highlight in yellow color. And we have now one constraint. Suppose the constraint is another surface, no? In 3D. Like that. Okay, no, actually like that. It's like that. And touch here. And now this is dotted line because it's invisible, and continue in the direction. Okay, this is the surface that represents the constraint. I want to call G in the language of the Lagrange multiplier. Is f and g, and f is the objective function. So the function that you want to optimize, minimize, f, and g is the constraint. Okay, so I need to find everything, maximum minimum. And so what's the idea behind Lagrange multiplier? Look, the idea is, suppose in the intersection here and between the constraints. This is the constraints. Okay, this is G. And the surface, I don't see. I see only in yellow. I select one piece to investigate this. I make a zoom. I make a zoom that part. So I make a zoom, two zoom. One zoom and another zoom. This represents that symbol, no? Okay, and we have here the piece of the curve that represent the constraint. Okay, remember this curve, que is the intersection is G, comma Y. Okay, now here exactly the same. And the surface you don't see because I make a zoom, so I see only is like that. Okay, entonces I using the famous gradient. Using the famous gradient of G and gradient of F. Now let's see what happens at the gradient. I select arbitrary point. Suppose 3 points. 1, 2, 3. 1, 2, 3. 1, 2, 3. So now, in this piece of curve, of course we have the tangent vector. And you know the tangent vector is always tangential to the curve. This is the famous tangent vector we study every day, R prime, because I parametrization this curve, no? And it's the tangent vector. Now, you know very well that the gradient is perpendicular. So suppose the gradient of the function G is always perpendicular to the tangent vector. This is G, sorry. G. Gradient vector G is a vector perpendicular 90 degree here. It's a vector here, 90 degree. Always 90 degree. It's a gradient G. Because I using the property for the gradient that always is perpendicular to the level curve. 90 degree. 90 degree. It's a 90 degree. Different situation happen in the gradient of F, not necessarily 90 degree. Is the gradient that we compute when you differentiate the formula, partial derivative, something. And one more time, we have here the famous tangent vector, R prime. But the situation, for example, in the gradient of the function f, que is the surface, you don't see clear because the surface I consider in yellow color, no? Pero I suppose hypothetically que es in this direction. Okay. And the angle is no 90 degree, it's theta. Okay, by the way, it's acute, less than 90 degree. Okay. And suppose que in this point, I skip one point, is like that. Suppose hypothetical, any direction. Entonces, this is obtuse. So I put it down. Entonces, you remember the directional derivative is in the direction u. Okay, in this case, the direction u that we are using in this analysis is the direction of the tangent vector, no? Of the function f is the dot product gradient, dot product r or unit vector. In this case, the unit vector and the direction for the tangent is the unit tangent vector. Entonces es obvio que this directional derivative in this case is positive because the angle is less than 90 degrees. And in this point, this is a point I want to call 1. And this point is point 3 because it's the point 2 I skip. So in the point 3, the directional derivative is negative because it's acute. And the cosine, one angle in the second quadrant, es obvio que es negative. Okay, entonces now maybe I am sure there are one point here in the middle in which is 90 degrees. And the directional derivative in this case is 0 in the point 2. Okay, so now the thing is, so you compare this sketch number 2 and sketch number 1. The thing is that in the maximum or minimum, the gradient of the function is parallel to the gradient of the constraint. So in other words, the formula que Lagrange discovered was the gradient of the function parallel gradient of the constraint. Cool. And how you translate an equation? Well, si es parallel, they are proportional. Entonces the formula is gradient of the function is equal lambda gradient of g. And who is lambda? Lambda is a famous Lagrange multiplier. It's a number. It's a number que don't have any important meanings, but this is a number. Okay, and this happens in the maximum or minimum of the any function. How we translate in the common language equations? Easy. You know very well that the gradient is partial derivative. Suppose 2 dimensions. Si es 3 dimensions, it's the same. This is the gradient, and this is lambda, and this is another gradient que es gx, comma gy. Okay, entonces si es equal each other, component by component, entonces es fx is equal lambda gx, equation number 1, partial derivative y is equal lambda, partial derivative g with respect to y, equation number 2, cool. However, professor, I have, suppose that when I set out this system, I have 2 equations only. Yeah, I have 3 unknown because basically the partial derivative of the f and the g depending on the x and y. So I have x, y, and lambda. It's a new guy. Okay, no problem. I know. Then the g, x, comma y gets the constraint equation equal to 0 is the third equation. And we solve the system. We determine the x and y value can satisfy this condition, and we determine the point. And as always happen in optimization, you evaluate the original function in order to determine if it's minimum or maximum. Okay, this is the idea behind Lagrange multiplier. Let's do in one example, only one. Let's see the animation to understand much better this idea. I try to explain here, but you see in animation in one specific example, and when you feel comfortable with the idea, in the review we have 1,000 problems with this. This is important, extremely important, extremely important. Let's see the first example. Okay, cool. Look, example 1. By the way, it's the only one for the moment. We have function, so basically is obtain the extreme value of that function. Suggest. So you write the constraint. The constraint is G. X comma Y equal to 0. This is a typical format for the Lagrange multiplier. You define the function f, que by the way is like a 0, and the constraint is, in this case, in this example, is x squared plus y squared equal 1. No? And the format of the Lagrange, you put in implicit x squared plus y squared minus 1 equal to 0. Okay. So we need to maximize or minimize. So find the maximum log extreme value, extreme, of that function subject to this constraint, so inside this constraint. Okay. You find the partial derivative of the x, partial derivative of the y, get to the component of the gradient of the function original, and the gradient of the constraint, exactly the same. It's doing. Okay, this is partial derivative this with respect to the x and y. Partial derivative this with respect to the y is x. Partial derivative g with respect to x is 2x. Partial derivative g with respect to y is 2y. Okay, okay. The Lagrange say, well, this component f of x is equal lambda times 2x. Okay. And f of y is equal lambda again times 2y. We have one equation, we have two equations. The third equation is x squared plus y squared minus 1 equal to 0 or equal 1. It's the same, equivalent, algebraic. And this is my system that I need to solve. In this case, it's super easy. I select this example to don't complicate your life with the algebra, no? But sometimes the majority of the scenario, even the example extremely easy, the algebra heavy. Therefore, I want to explain how you skip this algebra using Wolfram alpha. But it's okay. Let's do this by hand, que es super easy. One traditional strategy is, wait. Okay, I forgot something important. I forgot something important. Who is that? Who is that? And who is that? This is y, and this is x, right? Okay, I copy f of x. No, y and x. So this is my system. So one frequently strategy is, remember, I don't lie lambda. Lambda is not important for me. The important is the point, and the point in the space is x comma y comma z. So lambda is a multiplier que introduce Lagrange, pero I don't care. Well, I care, but not too much. So now, one strategy is if you divide equation 1 divided by equation 2, for example, it's obvious lambda is cancelled out. So it's y over x is equal lambda cancel is 2, and 2 is also cancelled, is x over y. Wow, it's easy equation, cross multiply, y squared is equal to x squared. Therefore, I can infer that x is equal to y. The point is satisfied. Our system is when the x and y component is the same. Bueno, si this is the same, entonces I plug it in. And the third equation, entonces x squared plus x squared again, because x and y is the same, no? Is equal 1. 2x squared is equal 1. X squared is 1/2. Therefore, x is square root plus or minus, no? 1/2, que es radical 2. After you rationalize, no? Therefore, the famous point that we have in my hand is radical 2 over 2, comma, radical 2 over 2, because I know that this problem x and y is the same. Plus and minus, every combination. Negative radical 2 over 2, comma, negative radical 2 over 2, and negative radical 2 over 2, comma, positive radical 2 over 2, and radical 2 over 2 positive, comma, negative radical 2 over 2. And you evaluate this point in the function. What function? And the objective function, and the function that you want to maximize or minimize. In F. You evaluate in F, you evaluate in F, you evaluate in F, you evaluate in F. But it's super easy because it's just multiplication, X and Y. This is radical 2 times radical 2 is 1/2. 1/2 positive, 1/2 positive, 1/2 negative, and 1/2 negative. Because the opposite side, no? And this is the maximum, and this is the mean. End the story. I finish. However, I want to show you now. Well, I want to show you two things. First of all, let me see where did the x squared plus y squared come from again. Well, this is the constraint equation. So this is the constraint equation. So x squared plus y squared is the constraint. Okay, guys, let me show you the algebra, and one picture is much better than 1,000 words. Okay, let me try. Off. Your algebra is frozen. Don't save. Okay, let me open again. Open. Okay, cool. Gradient is this guy. Lagrange multiplier. Cool. Okay, share the screen. Switching to that. You see now, super clear, because it's animation. At the beginning, you say, whoa, what the hell? I don't understand anything. Okay, look. We have the function f, okay, the blue, that function. We have the constraint, que es x squared plus y squared equal 1, que es the cylinder, no? Okay, remember, cylinder is the constraint. This is G, and f is the function. And the intersection between the function and the cylinder give me a curve. Now I create here animation to illustrate very well the famous 4-point that we found in this problem, okay? P1, P2, P3. Of course, I found x and y, but z was plugging in the original function, 1/2 positive or 1/2 negative. And you see, look, let me show you. Es obvio que en red color we have the gradient of the constraint, que always is perpendicular to the curve. However, in blue color, I put the gradient of the function, que no necessarily is perpendicular, it's in any position. But you see magically how in the critical point, in this maximum or minimum, they are parallel, maybe in opposite direction or in the same direction. By the way, when it's in the same direction, it's maximum. And when it's the opposite direction, it's minimum. Do you see clear? Like a water? Okay. Recap. We have, okay, look at that. This is minimum, opposite direction. And this is maximum, same direction. Be great. Cool. Okay, let me recap. Remember, this story begin. Okay, we have a function. Bang. By the way, this is the hyperbolic parabolic. Okay, and this I need to optimization this, but subject to the one constraint. That's mean that the important part for me is the part inside the constraint. The part outside, I don't care. Right? Now, this is the problem. So now, using Lagrange multiply, you compute the gradient of the surface. You compute the gradient of the constraint. Yeah, I know, according to the Lagrange theorem que they are in the maximum and minimum, they are parallel, maybe in opposite direction or in the same direction. And lambda is a factor, is a multiplier que give me in the point where the, for example, approximately the red vector is twice the blue vector. So lambda es 2, I guess so. Lambda is 2. Pero no, let's compute it now, lambda. Bueno, you can, pero it's not important. Lambda is not important. Do you understand or no? Now, clear, more clear or no? I have a question. Super, this is David is clear. The rest of the students. David, you are the guy que always Alvaro is clear. Okay. But I want to show you more. I want to show you more. Okay, let me try to go to the whiteboard again. I want to show you more. Do you see whiteboard? Not yet, no? Do you see whiteboard? Sometime in the review. Okay, yes. And in the review also, wow. This system 1, 2, 3, sometimes it's 4 equations, depending the amount of variables, it's 3D or 2D. It's very complicated solving by hand. I try to do my best in the review. However, you help me using Wolfram Alpha. Wolfram Alpha. We can use a Wolfram Alpha. We can use a symbol. I recommend Wolfram Alpha. I don't know. You know, some people create a habit. No, so now my habit is Wolfram Alpha. I consider it as the best option. Okay, so what is the idea of this? You go to algebra. I want to show you in few seconds. I want to go to the section of the algebra in Wolfram Alpha. Wolfram Alpha is a software, online, free, you know. And you go to the section of the algebra and you select solve. And you solve any equation. You solve any equation or any system. In our example, I copy this system exactly the same. Look, I copy y, this equation. Y is equal lambda, no Greek letter, but it's okay. I put L. I copy 2L times lambda. Very important, very important. And between number and variable, not necessary specification, default, Wolfram Alpha understand que es time, ¿no? Pero en between variable and variables, you put L times X. Wolfram Alpha believe que L times X is not L times X, es LX is a new variable. So no good. Now you write like that. So you now put a space. This is symbol indicate space. Okay, and you put on because that's the system. No? Let's satisfy the first equation, satisfy the second equation, gets X equal 2L multiplication Y. Okay, be careful with the time, it's important. And finally, is the constraint is X squared plus Y squared equal 1. And you press the button here equal, and Wolfram Alpha give me the answer. Let's do it now. This is one way. There are many ways in Wolfram Alpha to do this, but at least to understand one way, and you avoid the stupid algebra that is heavy and no intuition, no systematic. So now, depending of the problem, let's do it. I want to open my Google Chrome. I put Wolfram Alpha, and the review packet. I would like everyone follow me. No, you pay attention. Wolfram Alpha. Wolfram Alpha. Okay, I want to share the screen because I would like you see that. Let me try switching to Wolfram Alpha. So I open my Google Chrome or any browser, no? Entonces now I saw here. Do you see Wolfram Alpha? Do you see the no Wolfram Alpha? Do you see the page Wolfram Alpha? You see or no? Yeah. Okay, cool. Now you open that. It's the computational intelligence. Bam. And you go to the algebra section. Bam. And you take one box, either way, que contains solve. It's the command that we need to use. And you delete everything. Not the word solve. Delete the equation que is example in the Wolfram Alpha. I put my own equation. Okay, my own equation, remember, is y equal to capital L. Doesn't matter it's capital, no? But I decide capital. Multiplication, this multiplication is super important. X. You put a space. You put you put a space. And you put now x equal 2L times y, no? And my last equation is space and x squared, no? X squared, x power you indicate using this symbol plus y squared done. I press the button to solve it. This button, red one, compute input. Wow. Entonces, this give me the equation to verify that we are doing well or no. And also the value of the x and y gets important. And also the value for the lambda. Lambda is 1/2 or negative 1/2, depending, no? And the, let me see, and the minimum, que es negative and positive, alternating the sign is the x and y, lambda is negative. But it's not important. This is negative indicate no minimum maximum. Well, indicate yes, but it indicate opposite sign. When the vector is in the same direction, so two vectors can parallel. And for example, one vector is double. One vector is double. Then the other, entonces es positive 2. Pero si es in the opposite direction, es negative 2. Entonces that indicate que, okay, do you understand very well this or no? This is important. Extremely important, extremely. This is mandatory question in the homework and the test. Do you understand very well Lagrange multiplier? Okay, we come back to the web bar. Okay, super cool. I promise in the review we practice. Not today, I suppose. Okay. I'm okay. I am here. Erase everything. We start review, guys. From the beginning. Beginning. Well, not necessarily beginning because the question is, you know. Okay, question one in the packet I sent today. Okay. Don't expect super complicated. No. But it's important that you understand the concept. So I try to the algebra, not too long algebra. Suppose compute this limit. When the x comma y approach to 6,3. Entonces the function in the argument of the limit is x times y times cosine x minus 2y. Entonces, as always happen, when you compute the limit, you plug it in. If the answer is a number, we finish in the story. And this is good candidate to be like that because we have polynomial function xy, degree 1, and cosine. Cosine is continuous function. So everything is nice in this example. But when you plug it in, see, when you plug it in, the answer is indeterminate, 0 over 0, infinity over infinity, or another indeterminate. Entonces you need to manipulate in order to eliminate or no the indeterminate. Entonces you plug it in. Entonces the answer is 6 times 3 times cosine 6 minus 2 times 3. Okay, 6 times 3 is 18. Cosine something. 2 times 3 is 6. 6 minus 6 is 0. Cosine 0 is 1. The answer is 18. Finish. Okay, this is important for me. Okay, you understand that 99% of the scenario, when you see polynomial, sine, cosine, one rational function, but inside the domain, it's just plugging in. It's just plugging in. So one weird cases, no. One weird case is indeterminate. So now you see in the lecture, okay, it's very frequently this indeterminate in 3 dimensions fail at least 1 dimension. Entonces the limit do not exist. This is the question 2. The question 2 is limited. So do you understand very well the equation 1, I suppose, right? X comma y 0 0. Okay, entonces es the argument of the limit is 2y x squared divided by x to the 4th power plus y to the 2nd power. Entonces remember we plug it in. We plug it in, and obviously we have 0 divided by 0, que is indeterminate. Indeterminate don't means que do not exist. No, indeterminate is que you don't know. I need to do something in order to determine. Maybe determine is one number, 40, 20, infinity, 0, -1, or do not exist. So one traditional way is, travel in any direction. No create y0, x0. This is stupid. A line mx, right? Entonces you convert the problem in 2 dimensions and 1 dimension. Calc 1, limit, only one limit, when the x approaches to 0, of replace y for mx. This is 2mx cubic divided by x to the 4th power plus m squared x squared. Now, factorization. Well, okay. I don't want to copy again the stupid word limit. No. I know that this derivative in another expression que is factorization in the bottom at least x squared, okay, s squared plus m squared, no? And you cancel out x squared and 2 here, and stay alive only 1 in the top. So my answer is, I don't know, I put 3. I come from this 3 is 2. Is 2mx over x squared plus m squared. Okay. Entonces now when you get this answer, no problema. I restore, I erase, for example, that part and work on this. Entonces now we have a limit, in this case single variable of this guy, 2m x over x squared plus m squared. And you evaluate, it's obvious que 0 on the top and mx squared in the bottom, and the answer is 0. But this is not enough. So for any line you approach it, doesn't matter the inclination, the limit look like exists, yes equal to 0. However, I need to try for the parabola. Or not necessarily parabola, another curve. See, at least one curve failed, so you prove que do not exist. And this is the objective of this question. Okay, why is parabola? Because when you replace here y x squared, es obvio que the degree of the numerator is 4, 2 plus 2. And when you replace here x squared, double square is 4. Degree 4, degree 4. This is important to keep in mind. So my limit now, when you replace in this expression y for x squared is 2 x squared is x squared divided by x to the 4th power plus x squared is squared. So in the top we have 2 x to the 4th power divided by x to the 4th power plus x to the 4th power. So it's 2 x to the 4th power over 2 x to the 4th power. Wow, everything is cancelled, the answer is 1. So I prove that my limit is equivalent, algebraically of course, and is limited. Limited when the x approaches to 0 of the constant 1 is 1. Wow, si es 1 y es 0, es different value. Therefore, the conclusion is do not exist. Do you understand very well or no? This is classical. Similar problem you see in the test guide. Entonces, one fantastic clue is try to manipulate the substitution. But you try the line always. See, the line is depending of m. Entonces, you see que do not exist. Entonces, now one strategy is create substitution in order to put the degree of the numerator equal the degree of the denominator. See, it's impossible or no? It's okay. So far it's clear. So far we have 100 points in the test.
Professor.
Yes. Sorry, I erased.
Come on. If you chose a different line, like you chose y equals mx. If you chose like y equals x cubed, you could also use that to prove that the limit doesn't exist.
Absolutely, yeah. Okay, my recommendation is you try the substitution y equal mx. In this case, was always 0. That means for any line you approach it to the origin, 0,0, the limit is the same. Nice. However, it's not enough because you need to prove in any directions. Because in any direction, well, to say I recommend parabola. But what is the reason? One of the reasons is because we have a rational function. I need to create one substitution in order to put the degree of the top equal the degree of the bottom. Entonces now I using y equal x squared. When you put everything together, so when you substitution, when you replace y for x squared, now the monomial in the top is x to the 4th power, and the binomial in the bottom is x to the 4th power. And magically, wow, cancel out everything. And the answer is not 0, it's 1. Therefore, not necessarily it's always a square. Maybe it's a cubic parabola, depending on another example. Pero no. In the test, I put the traditional example. No complicate your life for the super sophisticated something, right?
And if they were equal, is that enough to say that the limit does exist?
Entonces, si suppose que es 0, when you are doing the substitution of the parabola, you need to continue to investigate. Okay, one possibility is using the more efficiency strong method, que es, for example, the squeezy theorem, or polar, okay?
So if you got like, if you had the line y equals mx and you plug that in and you got it to be 0, and then the y equals x squared and you got that one to also be 0, then you would need to either use the squeeze theorem or transfer everything into polar coordinates.
Exactly.
And then if that also equals 0, then the limit exists and it's 0.
Exactly. Good.
Okay.
But this new method, polar or squeezy, it gives you directly the answer, right? But you don't try it because it's a little bit, you know, nasty, sophisticated, you know? The squeezy is the most sophisticated. It's hard to see exactly what is the. Remember, the squeezing is you find two functions gets bonded, they're reaching a horrible function. Okay, I cannot compute the limit. However, you manipulate algebraically using your common sense, your logical two function, and you apply the limit and the two bonded, que es easier than the original, and you get the same value. Entonces now you infer que the horrible function is, I don't know, 0, 1, okay? Okay? What's your name, mister?
Max.
Max, okay. Let's move on to the question 3. Question 3 is super easy. Question 3 is super easy. So question 3 is determine domain and range of the function. Okay. Es always is given, for example, function que contain square root or not necessarily square root, division or logarithmic something, no? Que es the special function que have constraints, no? Okay, now for example, you take the expression inside the square root. Entonces I know very well that expression should be non-negative. Non-negative. Okay, entonces it's easy because I know very well. Okay, this is y greater than or equal to. And this is a little bit more complicated, but no big deal. You factorization. It's called algebra. Okay, here I discovered, well, using the change of sign method, no? -2, +2, and you evaluate, for example, in 0, in 3, in -3 and +3, and you determine that this is positive, this is negative, and this is positive. Therefore, the solution is solution is for x greater than or equal to, or x less than or equal minus 2. Okay, the part when it's positive, no? When it's positive, the expression inside the radical, the solution is real. Si es negative, it's imaginary. Okay? Entonces now we finish, well, almost, no? We can indicate analytically or graphically, or both. For example, domain, que obviously is a subset. Domain is subset of the R2. It is then x, y such that, bueno, y is greater than or equal to, and x greater than or equal to, or x less than or equal minus 2. Okay? So maybe it's in this or in this, pero satisfy this condition. And the range is obvious que es the range is always subset of the R square, so it's one dimension. And the C value such that C is always greater than or equal to 0. Because I suppose that this square root give me a positive number, right? No negative, no plus or minus. Okay, one picture, because the problem this is find the domain and function, express it using set building notation and graphic this. Okay, let's do a graphic. Graphic is xy is positive 2, negative 2, and y is greater than 2. 1, 2. Okay, so then I suppose it's this part and this part. Okay. This is the range. Domain is pretty easy. This is domain, sorry. The range is not necessary to do the graphics. Just the numerical line from 0, including 0, of course, to infinity. Cool? Any question, guy? Wow, we're doing fast. Good. I like that. No problema. I can erase the board. Everyone follow me? David. How did what? David, what is the question? How did? What part is confused? David? How do you find the range? The range is always easy because the range is the C value, and the C value is this function. So this is C value, C equals something. So I investigate what happened with the function. This function is obvious, always positive because square root, so what is the best? Is 0. Suppose 1 point here in the corner here, or in the corner here. Que es 2. This is 0. This is 0. And 0 plus 0 is 0, no? So this is 1. And I can see I do no specification square root plus or minus. Okay, so now it's only positive. It's only positive. It's a real number positive. Clear? Clear or not? Okay, super. Okay, let's move on to number 4. Okay, super easy. Number 4 is super easy. It's compute the second derivative. So second derivative of what? Of the function is number 4, no? Question 4. Question 4 is one function in 2 variable is given is x squared plus exponential xy. I need to find what the question say. Find the second derivative of this. Okay. My final goal is fxx, fyy, fxy, and fyx. You know, it's the same, but it would be good to compute to verification that we are doing well or not. And to find the first derivative, the second derivative, we need to find the first derivative. Okay, first of all. And the derivative of this with respect to x is 2x plus, remember, derivative exponential when this e is the same, but apply the chain rule, you differentiate with respect to x, the argument is y, a multiplication. The derivative with respect to y, that part is 0, because depending on the x, and here is similar, exponential, xy, and derivative with respect to y is x. Boom. Any question? First derivative. Okay. No? Let's move on to the second derivative. Second derivative with respect to x. Of course, I take the first differentiation y I differentiation again with respect to x. Entonces es obvio que es 2 alone. Deriva de 2x with respect to x is 2. Plus, you consider que y is a constant. And you differentiate, this is the number that we put outside the game, y. And derivative, this with respect to the x is e to the x, y. And derivative the argument is y, and this y multiply another y, and we have y squared. Everyone follow me? Guys, it's important for me that you understand very well partial derivative. And this is super elementary. Okay, it's the same thing on the calculus 1, but under the supposition that another variable, because you don't differentiate, you consider like a number. Fyy, say que David is x squared e to the xy. Everyone is agree with David? That you differentiate this guy? Yes, Ernest. Who helped me with the other? Well, the other look like a little bit more complicated because you differentiate with respect to x, and now you differentiate with respect to y. Who helped me? Be careful because you need to apply product rule like this. But when you differentiate with respect to, suppose you take this and you differentiate with respect to y, it's obvious that the first part, 2x, is gone, disappear. And you focus it in the derivative of this with respect to y, and you apply, of course, product rule. So the derivative y with respect to y is 1 multiplied by the exponential. Okay, I don't touch for a moment, no? Plus the derivative, the exponential, bueno, es y alone, I don't touch the y. Because I am differentiating with respect to x, no? No, the y. Entonces, I did that. Entonces, y stay, now you differentiate the exponential, no? The exponential is e to the xy, and differentiate this with respect to y is x, something like that. I'm putting alphabetic order, it doesn't matter, it's not important. Was good or no? I need to explain again or no? Just in case, we can verification. See, you differentiate this with respect to x, because I did the derivative with respect to y, I did that part. Now I need to differentiate with respect to x. Entonces es obvio que es product rule. Derivative of x with respect to x is 1. I copy this function. Plus, now differentiate with respect to x, que es x, and this is e to the xy, and derivative with respect to xy. Wow, cool. Same answer. Any question? How do you feel in that part?
Professor? What is fxy and fyx?
Your question
like, is that the derivative of the original function, or is that like a partial derivative?
Yeah, it's partial. It's second derivative. O sea, your question is, what is x this? What means that?
Yeah.
No?
Yeah.
Is. Okay, is. Let me use in the other notation to clarify this idea. It's second derivative of the function. You differentiate first with respect to x, and you differentiate after with respect to y. So to compute that, you differentiate the function, the original function, with respect to x first. The idea is here. Now this is partial derivative of the x, of the f with respect to x. Now, this notation is you differentiate now with respect to y, this guy.
Yeah, I get that, but I just like were we at? Is the question to just find all the partial derivatives?
See, the question is find the second order derivative of this. This is the answer key they want.
Oh.
This is
the second
answer.
Partial derivative.
Yeah, yeah,
all of them together. All of them together
yeah.
or the whole
Yes,
derivative?
Yes.
Okay.
Only that. Unfortunately or fortunately, we need to differentiate. So you need to find the first derivative partial to get. Suppose I complicate your life. I put computed the third partial derivative. It says f(x)(x)(x). Wow, what the hell is a third derivative of the function with respect to x. And you need to differentiate 3 times with respect to x. And there are many combinations. Cool.
Clear.
Super. Any other question? Remember, this is a review. This is another lecture. So you feel free to ask me any question. Any question. I never consider my student question is stupid. No, it's smart. It's your question. It's the part that you don't see very well. Maybe the notation is confusing. I understand this. Notation is confusing. Okay. Now number 5 is a long question, but I want to start. Go ahead.
That last part you put, the third partial derivative with respect to x?
No. I explained this, to see that in this case they want only second order derivative.
Okay.
Second order, no third order. Okay, question 5 is about chain rule. Let me try to start, and also we're spending for the next class. Well, it's given z is equal x cubed plus y cubed, semicolon, x depending of u and b, u times b, and y depending of u and b. And they want you find no second derivative, no first derivative is z with respect to u, and partial derivative c with respect to b. So my problem is we have one function c that depending of x and y. It's like a two intermediate variable. And the equation connecting x and u and b is this equation. So actually, my independent variable is u and b, no x and y. So this is dependent ub, and this is dependent ub. This is my tree que represent the chain rule. Okay, entonces, let me try to derive the equation and end the story. We are doing in next class. They want this. So partial derivative is z with respect to u. If you navigate from c to any u que you have in the tree. Okay, obviously it's this path and this path, this path and this path. Entonces partial c with respect to x time partial x with respect to u plus partial c with respect to y time partial y with respect to u. Yeah, I finished the u part. And the b part is similar. B is in this direction, in this direction, in this direction, in this direction. Partial c with respect to b is partial c with respect to x. It's a coincidence. This is exactly the same. But now this no. Time partial x with respect to b plus. This is exactly the same path. But this no. This is partial y with respect to b. Cool. Yes or no? And the rest is mechanical. You compute separately any partial derivative in the tree expression and put together. And final answer, I need can you express the answer using only like a function of the independent variable u and b, and disappear the variable x and y because it's intermediate. Clear? Let's do it next class. Okay.
Professor?
Uh-huh.
So the whole derivative is both of those partial derivatives, right?
Yeah, the whole derivative, the total, is everything. Okay, because it's because it's very, very complicated composite function. It's exactly the same we are doing in Cal 1. In Cal 1, for example, we have, let me do quickly, is you have, for example, sine y equal sine x squared squared. Or let me complicate, cubic. Entonces now, what is the chain rule in this case? Well, the chain rule is, well, okay, you can create intermediate variables. Suppose we have y equal u cubic. And I call u like a sine x squared. It's a composition. As you, okay, of course, in Cal 1, you are doing mechanical. Mechanical because you don't do this complicated tree. No. You also you differentiate directly here, proceeding from the outermost function, que cubic, the cubic first, sine second, and square last. In this case, more complicated. But this is a good conclusion. This is the, you call total, overall derivative. Overall derivative. Okay, guys, too much. We continue Monday, no? Monday is important day. Okay, have a nice day, everyone.